Grounding plastic injection machines presents a challenge that requires balancing manufacturer specifications with electrical safety codes. The core issue revolves around minimizing ground loop currents while ensuring adequate protection in the event of a short circuit. The manufacturer's recommendation for separate ground rods at each machine aims to reduce ground loop currents. However, this approach conflicts with the inspector's concerns about potential current flow between these separate ground rods, particularly if a short circuit occurs. The inspector's concern is valid because if a fault develops, the fault current could potentially travel through the earth between the separate ground rods, creating a hazardous situation. The National Electrical Code, or NEC, generally favors a single, well-established grounding electrode system to minimize voltage differences and provide a clear path for fault current back to the source. The fact that the main distribution panel, or MDP, is 400 feet away introduces additional considerations. A long grounding conductor can exhibit increased impedance, particularly inductive reactance, at high frequencies, which can impede the flow of fault current and potentially delay the operation of overcurrent protection devices. Several solutions can be considered to address this conflict, each with its own advantages and disadvantages. Firstly, using a single ground rod with a grounding conductor. This involves installing a single ground rod, typically near the main distribution panel, and running a grounding conductor from that rod to each of the plastic injection machines. The advantages of this approach are that it meets the inspector's requirement for a single grounding source and it reduces the risk of ground loops, as all machines are referenced to the same ground potential. The disadvantages are that it may not be as effective as separate ground rods in all cases, especially if the ground impedance is high and it requires a long grounding conductor, which, as mentioned, can increase inductance. To mitigate the inductance issue, it is crucial to use a properly sized grounding conductor. The size of the grounding conductor should be determined based on the size of the ungrounded conductors supplying the machines, as specified in NEC Table 250.122. Additionally, consider using aluminum or copper conductors, as their conductivity affects the impedance of the grounding path. Furthermore, the grounding conductor should be installed in a way that minimizes its length and avoids sharp bends, which can also contribute to increased impedance. Secondly, using a ground ring. This involves installing a circular or rectangular conductor around the perimeter of the area where the machines are located, and bonding each machine to this ground ring. The ground ring, in turn, is connected to the main grounding electrode system at the main distribution panel. The advantages of a ground ring are that it provides a more uniform grounding potential around the machines, which can help to reduce ground loop currents. It also reduces the likelihood of current flow to adjacent ground rods, as the ring effectively distributes the ground potential. The disadvantages are that it can be more expensive and time-consuming to install than individual ground rods, and it may not be feasible in all locations due to space constraints or other physical limitations. The installation of a ground ring should adhere to NEC Section 250.94, which outlines the requirements for grounding electrode systems. The ground ring should be buried at a depth of at least 2.5 feet and should consist of a continuous conductor, typically bare copper, that is at least 2 American wire gauge. The connection between the machines and the ground ring should be made with appropriately sized grounding conductors, and all connections should be made using listed connectors and methods. Thirdly, using isolation transformers. This involves installing isolation transformers between the power supply and each of the machines. An isolation transformer provides electrical isolation between the primary and secondary windings, which means that there is no direct electrical connection between the input and output circuits. This effectively isolates the ground of each machine from the common grounding system. The advantages of using isolation transformers are that it eliminates ground loops, as each machine has its own isolated ground reference, and it protects the machines from voltage transients and other electrical disturbances, as the transformer acts as a barrier to these types of disturbances. The disadvantages are that it can be expensive, as isolation transformers are generally more costly than standard transformers, and it requires additional equipment and wiring, which can add to the complexity of the installation. When using isolation transformers, it is important to ensure that the transformers are properly sized to handle the load of the machines and that they are installed in accordance with NEC Article 450, which covers the installation of transformers. The secondary side of the isolation transformer should be grounded in accordance with NEC Section 250.20, which specifies the conditions under which alternating current systems must be grounded. The recommendation for the best solution depends on the specific requirements and conditions of the installation. A thorough assessment should be conducted to evaluate the existing grounding system, the characteristics of the soil, the sensitivity of the machines to ground loop currents, and the available space and budget. It is recommended to discuss the options with the manufacturer, the inspector, and a qualified electrical engineer to determine the most appropriate solution. In addition to the three main solutions discussed above, several other factors should be considered. Firstly, proper bonding is essential for minimizing ground loop currents and ensuring electrical safety. All metal parts of the machines, including the frames, enclosures, and conduit, should be bonded together and connected to the grounding system. This helps to create a low impedance path for fault current and reduces the potential for voltage differences between different parts of the equipment. Secondly, surge protection should be considered, especially in areas where there is a high risk of lightning strikes or other voltage surges. Surge protective devices, or SPDs, can be installed at the main distribution panel and at each of the machines to protect against transient overvoltages that can damage sensitive electronic equipment. Thirdly, regular maintenance and testing should be performed to ensure that the grounding system is functioning properly. This includes visual inspections of the grounding conductors and connections, as well as periodic testing of the ground impedance to verify that it is within acceptable limits. The frequency of these tests should be determined based on the recommendations of the manufacturer and the requirements of the local electrical codes. Additionally, consider the type of electrical service supplying the machines. A separately derived system, such as a generator or an isolation transformer, may require different grounding configurations than a service derived directly from the utility. NEC Section 250.30 provides specific requirements for grounding separately derived systems. Furthermore, consider the presence of sensitive electronic equipment in the machines. Some electronic components are particularly susceptible to damage from ground loop currents or voltage transients. In these cases, it may be necessary to implement additional measures such as shielded cables or filters to protect the equipment. Remember to consult with the machine manufacturer to determine their specific grounding requirements and recommendations. They may have specific guidelines or best practices for grounding their equipment that should be followed. Consider the environmental conditions in which the machines are operating. In corrosive environments, it may be necessary to use special grounding conductors and connectors that are resistant to corrosion. Also, consider the potential for electromagnetic interference, or EMI. Ground loops can contribute to EMI, which can interfere with the operation of the machines. If EMI is a concern, it may be necessary to implement shielding or other mitigation measures. When selecting a grounding solution, it is important to consider the long-term costs and benefits. While some solutions may have a higher initial cost, they may offer long-term savings in terms of reduced maintenance costs, improved reliability, and increased safety. Remember to document the grounding system thoroughly. This includes creating detailed drawings and diagrams that show the location of all grounding conductors, electrodes, and connections. This documentation will be helpful for future maintenance and troubleshooting. Also, train personnel on proper grounding practices. Ensure that all electricians and maintenance personnel are familiar with the requirements of the electrical codes and the best practices for grounding electrical equipment. This will help to prevent grounding errors and ensure the safety of personnel and equipment. When installing grounding electrodes, ensure that they are installed in accordance with NEC Section 250.53. This section specifies the requirements for the location, depth, and spacing of grounding electrodes. Also, consider the soil conditions when selecting grounding electrodes. In areas with high soil resistivity, it may be necessary to use multiple grounding electrodes or to use ground-enhancing materials to improve the effectiveness of the grounding system. In addition to the NEC, other standards and guidelines may be applicable to the grounding of plastic injection machines. These may include standards from organizations such as the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA. Consider the impact of the grounding system on the overall electrical system. The grounding system should be designed to work in conjunction with the other components of the electrical system, such as the overcurrent protection devices and the surge protective devices, to provide a comprehensive protection scheme. Also, consider the potential for stray currents. Stray currents are unwanted currents that can flow through the grounding system and can cause corrosion, interference, and other problems. If stray currents are a concern, it may be necessary to implement mitigation measures such as isolating the grounding system or using specialized grounding techniques. When making grounding connections, use listed connectors and methods. This ensures that the connections are reliable and that they meet the requirements of the electrical codes. Also, protect grounding conductors from physical damage. Grounding conductors should be installed in a manner that protects them from abrasion, impact, and other forms of physical damage. Remember to coordinate the grounding system with other trades. The grounding system should be coordinated with the other trades involved in the installation, such as the mechanical and plumbing trades, to ensure that there are no conflicts or interferences. In some cases, it may be necessary to use specialized grounding techniques such as equipotential bonding to minimize voltage differences between different parts of the equipment. Equipotential bonding involves connecting all metal parts of the equipment together with a low-impedance conductor to create a common ground potential. This can help to reduce the risk of electric shock and to improve the performance of sensitive electronic equipment. When designing a grounding system, it is important to consider the potential for future expansion or modifications. The grounding system should be designed to accommodate future changes to the electrical system without compromising its effectiveness. Also, remember to comply with all applicable electrical codes and standards. The grounding system must be designed and installed in accordance with the requirements of the NEC and other applicable codes and standards. This is essential for ensuring the safety of personnel and equipment and for complying with legal requirements. The grounding of plastic injection machines is a complex issue that requires careful consideration of various factors. By following the recommendations outlined above, and by consulting with qualified professionals, it is possible to design and install a grounding system that is safe, reliable, and effective. It's always important to have any grounding system design and installation inspected and approved by the relevant authorities to ensure compliance with all applicable codes and regulations.